Okay, guys. All right, so let's do this. So, so the idea is, as our yo-yo moves down, we're converting gravitational potential energy into both rotational kinetic energy and regular kinetic energy, yes? Good? Okay, so when you have the yo-yo at the top, guys, can we call it the... And also, if somebody in front of you is wearing a hat you can't see because of it, let them know. Be nice. Take off the hat. Okay? All right, and also, I guess while we're talking about the hats, two quick things about the hats. One, the school does have a pretty, I think, preposterously, this is on video, so you can blackmail me. A very strict hat policy, which I think is weird. But whatever, I don't make the rules, so it is what it is. So you can't wear the hats in the halls. All right? I know, it's a thing. You are more than welcome to wear it in my class every day. Okay. On the day of the AP test, you are welcome to wear it all day. In other teachers' classrooms, you'll have to get the teacher's permission. Okay. I'm guessing that you probably need to take it off in other teachers' classrooms. Would be my guess. But you can wear it in the halls on the day of the AP test. All right? Good? Same thing. I think same thing on the final. All right? Clear? All right. The one other thing that you should be aware of with the hats, you guys, is that if you're gonna wear the hats, so physics is always a good, right? But you should also know at least one trick. You should be able to pull a rabbit out of your hat. All right. Okay. All right. So back to this. All right. So as the yo-yo moves, we're going to be converting gravitational potential energy into both kinetic energy and rotational kinetic energy, right? Okay? So our GPE is just mgh, right? Our KE is just 1/2 mv squared. All right? Now, we can't just do beta times KE on this. Because, how do I want to say this? The rotational inertia of this thing isn't just beta times mr squared, because there are two different radii to take into account. There's a big radius and a little radius. Does that make sense? Okay, so there's actually two different radii. All right, so the way that most of these problems will be set up is they'll just give you numerically. They'll say the rotational inertia of this thing is, and they'll give you a number. Follow? Okay? So because we've got that, that means that to calculate the RKE, we're going to have to do, we're going to have to do 1/2 I times omega squared, right? Good? McKeever, there's a seat up front if you want. Since Cullen's being a poop. What else? Take that! All right. Hi, how are you? Good. Hi, Mr. Hecker. Never been here before. It's nice to meet you. All right. So here's the big difference, you guys. Here's why this example is different than the one that we did yesterday. Yesterday, our object was rotating about its perimeter, right? Okay? So the radius of rotation was the same as the radius of the object. Now, that's not the case, right? So yesterday, we replaced omega with v over r, right? Today, we have to replace omega with v over little r. Does that make sense? Because the radius that it's rotating about is not the exterior radius, but the interior radius. Does that make sense? Yep. All right? So, this becomes mgh equals 1/2 mv squared plus 1/2 I times, I'm going to replace my omega with v over r naught. And the little drawing there shows you that r naught is that inner radius. Squared, thank you. Cool? All right, so now I'm going to algebraify this thing and use the same trick I used yesterday. Remember we learned that VF squared is 2a delta x?
Yes.
Okay, so I am going to, let's get rid of these 1/2 by multiplying by 2. That was weird emphasis. 2.
Kind of sounded wizardy, though. You should have left a write-in section for this shit. Like put like a note card at the bottom.
Nice. I agree. All right, so let's see. So then this is going to be v squared times m plus I over r naught squared. All right, I did a little bit of algebra there. I multiplied by 2 and then factored out the v squared. Good? All right, so if I divide both sides, then I get v squared is 2mgh over m plus I over r naught squared. We're almost done. Did I miss something? Everybody good? All right, cool. So remember from yesterday, since our VI is 0, this is really VF, right? So VF squared is 2a delta x, right? What's my delta x in this problem? It's the same as the height, isn't it? Follow?
What was that?
So from yesterday, remember that 2a delta x is VF squared minus VI squared, right? Our VI is 0, so this goes away. Our delta x is the same as the height that it's fallen. So this is h. I shouldn't have crossed it out. It's h. So v squared is 2ah. Everybody good? We're almost done. All right, so let's see what cancels out here. Let's see. Shh, we're almost done, you guys. The h's cancel. The 2's cancel. Oh, now I've got an equation for a. And it doesn't quite look like the equation on the sheet. It's super close, though. Anybody see? There's one more step to finalize it. How is that different than the one on the sheet that's sitting in front of you? We're not supposed to have that m on the top. We've got mg over some mess. So if you divide the top and the bottom by m, then it gives you exactly this. Cool? All right, so here's the deal, you guys. You should not memorize this. You know what I mean? Like, there's enough other garbage to have to memorize. All right, the big thing that I want you to understand from this problem is it's still just a conservation of energy problem. Okay, just like a ball rolling down a hill, same thing. With the one little exception is that your angular velocity depends on that inner radius, not the outer radius. I think if you get that, everything else is the same. Carl. Oh, gotcha. G is positive, so and your acceleration does need to be downward, so yeah, just tack a negative on. That's not very satisfying, is it? We know it's accelerating downwards. All of the numbers I used were positive. Okay, yeah. All right, questions, you guys? All right, any problems with what we did here with the yo-yo problem? Okay, cool. All right, so the last thing I want to do is show you, so this is a thing that, sorry, before we get there, real quick concept-y question. Take a second. So it says disks A and B are identical and roll across the floor with equal speeds. Disk A rolls up an incline reaching a maximum height h. Disk B moves up an incline that is identical except it's frictionless. Is the maximum height reached by disk B greater than, less than, or equal to h? Think about it for a minute by yourself. Think about it for a minute by yourself. You might need to scribble on a piece of paper. I know I did the first time I thought about this.
The one that was rolling that stopped rolling.
All right? And then once you think you've got an answer, turn to a neighbor and see if your neighbor agrees.
Right?
I'm not your neighbor.
Probably say the wrong thing anyway.
Such confidence.
Yeah, I think it's gonna be less than.
All right, so I honestly haven't stopped and taken a second to figure this out since I wrote this question last year. So somebody convince me one way or the other. All right, sure, what do you got, Adam?
It's going to be less because for A, the RKE...
Which is going to be, B is going to be less?
Yeah, B is going to be less because for A, the RKE is transferred over to GPE to give it like a bigger height, whereas for B, it's just going to keep, like in a perfect world, it's just going to keep rotating and not stop. It's not going to help get it any higher because there's no friction.
I gotcha. Does anybody disagree with any of that? That makes sense. Margaret?
I have a question. Can
Yeah.
it not roll without friction?
Say that again?
Can't it not roll without friction?
It can't smooth roll without friction. So let's take a quick second and talk about that, you guys. So there's a difference between rolling and rotating. Okay? So the one without friction, it's already rolling when it gets to the ramp, right? So it gets to the ramp, it's already rolling, right? Okay? If there's no friction, would it suddenly just like stop spinning? It's going to keep spinning, right? It's just not going to be rolling as it goes up the ramp, right? You see what I mean? So I want you guys to make sure you understand, when I say rolling, I mean moving and rotating without slippage, okay? I know slip is that word always sounds, it's like the new moist, right? All right, everybody good?
Yeah.
Okay? Are you good, Margaret? Okay. All right, somebody else had a hand up. Patrick, what do you got?
I'm going to say B is going to go higher because at first I thought they'd be the same because at the end they both stop rolling, so I thought they both had the same energy, but friction is a non-conservative force that pushes against its motion.
Okay.
So it should take energy out of the system.
So you're saying it's going to take energy out of the system, which would mean what?
It would have less final energy.
Less final energy.
Yes.
That makes some sense to me.
Wait,
Wait,
no,
what
no,
does-
Oh,
Wait, what doesn't stop rolling?
Daniel, what do you thinking?
Would it depend upon the coefficient?
Oh, the ramp is friction.
Higher.
I'm sorry, Daniel, what?
Would it depend upon the coefficient where a higher coefficient would be good, a stronger force of friction would be more work against the object that would eventually make up the difference of the fact that its RKE is also being converted and at some point would be the same, at some point.
So let's talk about, you guys have mentioned the work by friction. Is that what you want to respond to?
Well, like, kind of, because isn't it total kinetic energy equals KE plus beta KE? Is that
Yeah.
so it's
Well,
not-
oh wait, say that again.
the
Shh,
total
shh. Guys, please.
kinetic energy equals, oh no, beta KE equals RKE.
Yes, there you go.
So it's not like, it's not like there's not more energy. It's just rotating instead of just like going.
Okay,
And
so
because
which one's
it's
higher?
frictionless, it's like, so they have the same amount of the energy before they go off the ramp, but because there's no friction, like, there's not going to be any energy lost to where heat, that's where it goes, right? And so it's going to go higher up the ramp because it's not losing any energy. Whereas,
So you guys are all, I'm sorry, I'm totally stepping on your toes. I want to pause you guys for a second because some of you guys are headed down the wrong path here. Friction, so you said heat. How much work does friction do? There's an exact number that I'm looking for. 0. You guys remember why? Say that again? Because if it's rolling, huh? at the point of contact. So friction is applied right here, right? Friction is applied at the point of contact. What's the displacement at the point of contact? Zero. How much work does friction do? Zero. Our total energy is the same at the top and the bottom for both situations. Friction or no friction, our total energy is at the top is the same. Does that make sense? That is very important. All right. So let's just get through this because I want to make sure we get through the other example. All right. So let me give you two different explanations for how you can solve this. All right. So the first one, let's evaluate it just in terms of forces. All right. So both of them have some velocity at the bottom, right? Same velocity, right? Okay. For the one with no friction, what forces are acting on it? Gravity. Anything else? Nope, just the parallel, well, in normal force, but yeah. What forces affect its motion? Just that parallel component of gravity, right? Okay, cool. How about A? Let's see. A is also going to have gravity pulling it down, and friction. Which way will friction act?
Right?
Yeah, because the velocity.
No.
You're preventing it from sliding, right? So it's got to go down the hill,
It's the bottom of the wheel.
right? You're preventing the bottom of the wheel from sliding. Fingers crossed. So I believe that friction should be down the hill. So which one's going to have a bigger net force? A, right? Good. So that means that this one should have a bigger acceleration and should not go as high, right?
Oh, no.
No. I'm on team A.
Physics! Wait, so force of gravity.
All right.
They're the same?
Okay, so according to this analysis,
Oh, A is going higher.
A is going to have a bigger acceleration, it'll slow down quicker and not go as high, right?
Yes.
Okay, so let's analyze it in terms of energy. So in terms of energy, this guy is going to start out with KE at the beginning, and at the top it's going to have just GPE, right? Because when it stops, because of friction, it's going to slow down. When it stops, it's not moving and it's not rolling, right? Okay. And this other one, that same kinetic energy is going to get converted to GPE and RKE, right?
Isn't it switched? No.
Oh, shoot, this one had RKE, sorry. Okay, but my point is this one is still going to have some RKE when it gets to the top.
Wouldn't it have the exact same RPM?
Yeah. So this one's going to end up with less GPE at the top, right?
Okay.
So now I feel like that one shouldn't go as high.
Yeah.
All right, so one of my two arguments is wrong. What do you got, Daniel?
So, wait, from before with the acceleration thing or within here?
I don't know, you tell me.
So for the acceleration thing, I was thinking, for A, the force of gravity, or not force of gravity, the force of friction is causing an angular acceleration, but you were talking about it as if it was a linear acceleration, where that was lesser.
Well, there is a linear acceleration.
Well, there is, but it's also got a stop rotation, so it's kind of like a component thing, I guess, which wouldn't be the same acceleration
Okay.
as
Yeah. So the problem is the force of friction. Totally counterintuitively, the force of friction in this example is not down the hill.
It's generating a
It's
torque
up the hill.
clockwise
Because,
up the hill.
think about this. So suppose it's rolling up the hill. Okay, as it rolls up the hill, it has to slow down, right? Force of gravity is not going to provide any torque because it's at your pivot point, right? So which way do I have to push the bottom of the wheel to make it slow down? Ah. So this force of friction was wrong. Okay? So B should not go as high. Does that make sense?
Yes.
All right, that was a lot of work to get there. Questions on our process? All right, so this is big. This force of friction actually goes up the hill, which is really weird. Okay? And so what's happening is, what that's doing is it's serving to decrease the rotational kinetic energy and convert it to GPE. It's helping it climb the hill. Think about trying to climb a hill with no friction. It would be hard, right? That's what's going on here. Follow? Questions on it? Yeah, Daniel?
Also generating heat or no?
Nope. Because your total energy is the same. There's no energy loss. There's no work done by friction here. Yeah, assuming there's no sliding. Assuming there's no sliding. Yeah, Margaret.
Is that only when it's rolling that it doesn't release heat? Because like when you friction here, you're releasing heat.
That's because you're sliding. So the whole point of rolling is that you're not sliding.
See, that's where I was getting confused. I thought like when you said that you meant for like everything.
Gotcha.
But if it's just for friction, okay, that makes sense. Sorry.
Cool. All right, so how about heat over here? So it is sliding if there's no friction. Is there heat there?
Yeah. Well, though there's no friction.
Right. Okay.
There was then.
So there is one problem on your homework, and it's a really good one. I don't remember which number it is. I'll see if I can figure it out. Where you've got it. You know how when you throw a bowling ball, it doesn't roll right away. It slides for a little bit, and then it starts rolling. Okay. Maybe you don't know that, but it's a thing that happens. When you first roll a bowling ball, usually you let go of it, and it's just kind of flying through the air. It might be spinning a little bit, but it's not rotating at the same angular velocity that would correspond to its linear velocity. So it slides for a little bit until friction causes the linear and angular velocities to sort of equalize. So there's a problem about that on the homework. So it's a good one to do. All right. Any questions? All right. One last thing. All right. So here's so I told you before that to wear the hat you have to know a magic trick. All right.
How did you do this?
So here's my magic trick for the day.
You're gonna make more magic?
All right. So let's go back to this thing. All right. So I've got the string wrapped around. I'm going to put my pivot point in the middle. Okay. If I pull the string, which way will the spool rotate? Clockwise or counterclockwise?
Wait, which way? Like this?
I'm going to pull the spool this way. So from your perspective,
Okay, got it.
is it going to? That's why I'm trying to stand off to the side so I can see it too, so I don't confuse myself. Clockwise or counterclockwise? Oh yeah, that makes sense. All right, everybody good with that?
Yeah.
All right, I'm going to flip it over. And pull it. So now the string's on the bottom. I'm going to pull it. Which way is it going to rotate now?
Not counterclockwise.
Clockwise.
Boy, that's clockwise.
Oh yeah, that works. That works.
What?
Okay, all right. So that's cool. Did that all make sense? No. Oh, it's not yet.
It's not.
Not yet. This is the misdirect.
Yes.
All right. All right. So does everybody agree it did exactly what we expected it to do, right?
Sure. Have you seen the Prestige?
Yes. So good.
Can we watch it in here?
No. All right. So is everybody good? Does anybody disagree? It did exactly what we thought it would do, right?
Yeah.
All right. Okay. So let's try it again. The only problem is so this time it's just rotating sort of in free space, right? So what if we put it on a surface so that it's rolling? So let's do it again. I'm going to put it on the bench here, if I can get the bench level, and I'm going to pull the string. Come on. Okay, there we go. All right, so in a minute I'm going to pull the string. So just to be clear, it's over the top right now.
Okay.
Clear?
Yeah.
All right, so I'm going to pull the string. You didn't see that. I'm still working on my presentation of my magic tricks. Come on. All right, I know it's not easy. Okay, is it gonna roll, rotate, slide? What do you think is gonna happen? Discuss with your neighbor real quick. If it's gonna roll, which way? I'm gonna pull it gently. I'm gonna pull it gently. I'm just gonna pull this way.
Okay, so the string is pulling it this way, and grab.
Don't overthink it.
Don't worry, we will.
All right. So
I'm on slide game.
here are your choices. Just rotate, just slide without rotating, or roll. Okay? So, how many of you think it's going to just rotate without moving? How many of you think it's going to just slide without rotating? One? How come? Just cause?
Well, there's not a lot of friction. It's just,
Okay. Okay.
I don't know how
It's
they
gonna rotate and slide that way.
Okay. So, and then the rest, do you think it's going to roll? Point for me. Which way?
That way.
Okay, so if it's rolling that way, that means it's got to be rolling this way, right? Agreed? Anybody disagree? Great, let's do it. Are you ready? Are we watching? Here we go.
Oh my god, it's gonna go like, oh no.
Hey, hold on.
Wait.
What, if I yanked it? I don't know.
You gotta really yank it too. You gotta
roll.
You got a Yankee, that yank.
And now I'm comfortable with this conversation.
Yeah, now it's coming bad.
Come on.
You're what?
One is changed. Yeah.
Oh, that's good. All right, here we go.
Next time.
Oh.
Just move quicker. Okay. John, what, you were going to say something? All right. Okay, so. Yeah, let's flip it over. All right.
No.
So now I just got the rope on the bottom like this. I'm going to set it down, and in a minute, I'm going to pull the rope. Discuss with your neighbor. What do you think? Don't you cheat!
It rolled. It's rolling
Oh,
to the
okay,
left, and I'm trying to put it back.
Yeah, I
We're not talking about when the string stops. Let me just.
Won't be honest. What's the most of it?
All right, do we need more discussion time? Are we good? All right, does anybody think it's going to just rotate in place without moving? Oh, a lot of votes for that. Okay, who do we not often hear from? Brendan, talk to me.
Alright, well, you see, if you're pulling that way,
Yeah.
it's spinning that way, and therefore those two are opposite directions. Stop touching my head. It wasn't. It goes in opposite directions and then sort of stays there
Okay,
until the string runs out, then it's when you go for a twist.
okay, I gotcha.
Then it's going
Anybody think different? Think that for a different reason? Okay, so some of you guys think that the force this way working against the roll the other way, it's going to just, what did we decide? Roll without moving? Okay. All right, does anybody think it's going to just slide without rotating? No. All right.
the string runs out, yeah.
How many of you think that it's going to roll that way?
Yes, I think that.
Okay, Teddy, defend your answer.
Well, it rotated that way, and the other one rotated this way, and then it rolled this way, and I have to.
Okay, so you're saying that when we did it in free space, pulling it this way made it roll, spin that way, so it's going to roll that way.
I'm just gonna hope the friction's not go that way.
Okay, all right. So, but you're worried about friction.
Yeah,
Okay, I hear you.
not a lot of experience.
I want all of you to think about which way friction's going to act here. Yeah.
I was just thinking, like, when you pull it and you go around the bottom, it's kind of almost like it's going that way a little bit, like you're pulling it that way. I don't know. That's just like how I think about it when I do it. Let's do it.
Okay, so you think it's going to roll that way? Okay. All right. Is there anybody who thinks it's going to roll this way? Nobody? Yeah, why would it do that, right? Because if I do this, it rotates this way, right?
So now it's going to do that.
All right, are we ready? All right, you ready?
Yeah.
Oh!
Peter, I figured
Whoa.
Only because oh!
That kind of makes sense though. When I
Every
saw
time
it.
I do this, I'm surprised.
If you pull it that friction's actually.
Honestly, I first saw this like 10 years ago, and I was like, and it does exactly the. Stop rolling, you.
Whoa!
Cool? You know what else is weird? Because I don't know, maybe that one's not as weird. All right, so why does it do that? Anybody have any ideas? Who have we? Yeah, what do you got, Rhonda?
Since which way is it spinning? It's spinning this way, right? So yeah, it's spinning this way, so friction's gonna act that way, so it's gonna roll this way. No. Then
So you're saying that it wants to spin this way,
yeah, but you're pulling.
and
it that
friction's preventing that from happening by pulling
other way.
this way. Do you guys agree with that?
And you're forced to
What he got it right? We all freaking.
So let's see, it's sliding that way. If I want to prevent something from sliding that way,
Push that way.
oh no, friction is this way.
Yeah.
Shoot. I thought you were onto something. I genuinely did. Saba, what do you got? Wait for me to.
If you were holding it up in the air and you pulled,
I know, but I didn't call on you.
and you pulled the string, it would go up like a yo-yo. So even if you just like if you're pushing side,
That's not how that works.
yeah, if you pull it
That's
up,
not
it's
how
gonna
a yo-yo
come
works.
No,
Wait, no, you gotta do it, you gotta flick it, going around.
It'll come on taped if I do it.
So there's no force when you pull back up. If you
No,
had
no,
a
no,
yo-yo,
no, 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 no.
Let it
It
drop.
bounces out.
All right.
Have you never used the yo-yo before?
So let's, rather than comparing it to other situations, let's explore this situation, okay? Daniel, I haven't heard from you yet today.
So what I'm imagining is that so the solid string would have caused it to rotate that way. So friction goes that way, right? And then so you have these two forces trying to rotate in different directions, creating opposite direction torques. And then friction is operating on a much wider radius, so imagine that this creates a greater torque because of the rotating and thus roll that way.
Ding, 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 ding. Yeah, that's great. That's great. All right, so here's a simple explanation for why it does what it does. So the first time I did this, the string was over the top, yes?
yeah,
Do you guys agree that's basically the same as doing this, pulling from the top,
yeah,
right? And it rotates this way, right?
yep.
What if I pull from lower down? Still rotates that way, right? I'm still producing torque around this point.
Just smaller.
Just smaller torque, right?
Oh, the force.
Does that make sense? So that's exactly what's happening. Look, suppose I grab the wheel up here and pull that way. Suppose I grab the wheel down here and pull that way. Same thing, right? You're still producing, if this is your pivot point, you're still producing, your force is above that, so your torque is still whatever direction that is from your perspective. Follow? Okay? Now, you can, if we knew the rotational inertia of this, you can calculate the force of friction. It gets ugly, I'm not going to go through it. And let's see, it wants to spin this way, so friction's that way, right? Yeah, so you've got the rope pulling this way, trying to make it rotate this way, friction's trying to make it rotate the other way, and it turns out that the torque from friction will always win because it's got a longer radius. It is a slightly smaller force, but because of the longer radius, it still wins. Follow?
Magic.
Questions? I will be honest with you, I understand it on paper, I'm still surprised every time I see it. Okay? Like it's,
every time.
alright? Alright, questions you guys? Alright, so again, over the weekend you really got to get started on the chapter 12 stuff. Really at this point you ought to be able to do all of the 12-1 homework. The only reason I'm not assigning all of it is because it's giant, and it seems unreasonable to make it all due Monday. And you're going to have stuff due, look, you've got something due Wednesday, Thursday, and Friday. So if you leave that 12-1 stuff to Wednesday, you're going to be in trouble, all right? Questions? Well, the multiple choice part is due Wednesday, or Monday. The rest is due Wednesday. Okay?